I would like to call Mr. Pushkar Sheth on stage. So the next expert talk is by Mr. Pushkar Sheth of WebTech Technology.
So yeah, thanks for having me here. And I'll talk about what we do in CFD in our applications here. But before that, I'll quickly run through the company. This is my introduction. Chandan has already introduced me to everyone, so thanks for that. Um, so, so WebTech is a conglomerate. Started by Westinghouse, and then they bought out the Fevely branch, which is the transit engineering. So mostly all majority of the metro trains are from Fevely, some are from Alstom, and then they also bought the GE transportation business, the rail business of GE. So was air brake technologies, but that umbrella applies to everyone. And yeah, I am legacy GE. I joined GE back in 2011, and I've been working on diesel engine durability of all the GE components since then. So yeah, our freight headquarters, the GE Rail headquarters, are in Pittsburgh, Pennsylvania, in the US, and along with and maybe I can tell in detail or to relate with the audience. If you watch the Denzel Washington movie Unstoppable, so all the locos you see there, the few of them, I think BNSF was the customer there. So also in North America, huge deal in 2017 to supply railway. These are diesel electric locomotives. And so this is the engine family that we work on. I am a part of the base engines team. So the FDL is the legacy engine. They have been around for the past 50 to almost 60 years in field. Of course, they were a part of a different company back then, and then the design came to us. Then in 2003 to 2007, we started development on our GO Tier 2 and Tier 3 capable engines. So Tier 2 are emission norms for these diesel engines. So now currently we are at Tier 4, but not all the fleets have moved to a Tier 4 compliant engine, but we still offer the capability of Tier 4 capable engines. Um, we have applications in locomotives. As I said, the smaller variants of these engines are also used in marine industry, like big ships to tugboats as well. So we have an inline 6 variant and inline 8 variant, or a V8 variant of the FDL engine, which are used in tugboats on the Panama Canal. And of course power generation, so an engine can stay in place and then generate power using it. So yeah, this photograph is of our Indian Railway locomotive. You can see it in many media photographs also uh, around the media and social media. And other products are LNG. So dual fuel is something that we are taking up seriously again. Using methanol or ethanol in conjunction, in mixture with diesel spray. And then hybrid locomotive, so use a battery and a small engine. That is a proof of concept that we have delivered. An engine digital twin, now you can look at it in various ways. There are that can have a digital twin, but an entire locomotive engine uh, entirely built as a digital twin, we have not achieved that yet, and it will still take a lot of years to do that. Battery electric locomotive also, we have delivered a proof of concept. If there is a customer, we will definitely can supply there. Now, what are the basic parts of the engine? So, you see there the power generation piece, the V12 or a V16 engine. Coupled to that is an alternator. So we have our GMG series alternator. That is also either it can be bought out or we can also make alternators. And then the alternator supplies powers to IGBTs and then to traction motors. So that is how the locomotive runs. Okay. So what are the opportunities where we can use CFD or simulation as a whole to make this product a success? Okay, so let me go to the heart of the slides very quickly. So now how do we divide this? We can divide this by the product, or we can divide this by the timeline in which the simulation needs to show results. So the first category I would put at is problems. Now if we see some problems in field and we think that it is caused by a flow thermal problem in a component, uh, we need those results very quickly. As Dr. Ashok previously said, we need the results in 2 days, or in industry lingo, we need the results yesterday. So yeah, that is where the first category of results, right? And doing a CFD in that scenario is very difficult. So you generating a mesh itself takes a couple of days. So solving it is, questionable. Beyond that, you might also need to do further analysis. Like CFD will just give you the temperatures. You might need to take those temperatures to a structural model and then solve the structural for the durability, solve a low cycle fatigue code, and then say that yeah, this is the problem because of which the component is failing in just after installation. The loco is just rolled out of the manufacturing line and the components breaking. Now, the second category can be program based, where you have decided that you are going to use a simulation tool to help design your component. Okay. Now, this component can be designed in-house, or it can be a bought out component. It's very easy to start simulation on an in-house component because the CAD details are captured very easily. You can start the program in a very planned manner. If it's a bought out component, it gets a bit of a struggle getting the correct CAD for your variant of the part that is getting supplied to you. So yeah, that the program based analysis can involve CFD, can involve a further FEA if required, and that based on the budget and timeline can be 3 months to 6 months timeline. And further to this is 5 years down the line, what are we going to do? So that is a part of advanced engineering team that I work on, and that for that we do combustion. Like an example will be a combustion simulation. So where we do the combustion on the cylinder and then predict the emissions, although we are not there yet. And as far as tools at Webtech go, we are still with commercial tools. We don't use a lot of open form. It is almost close to zero. So I'm trying to pioneer open form into Webtech for simpler applications at first to prove the capabilities and then go to complicated applications. So let's go component wise. So a locomotive will have a major component of cabs, that are the sheets surrounding your components, and the diesel engine and attached components. Okay, so let's discuss on the cab side. The cabs will contain engine cab, radiator cab, and an operator cab. Now, major application of CFD that I learned from my colleagues is if you look at part of the locomotive is where the full structure platform is there. Now, thanks for keeping this board because it's useful. So you have the full platform, which is a couple of meters long. Okay, it will take you about 15 seconds to walk the length. Now you need to ventilate this because there are couple of motors attached below it. Okay, so how do you optimize this design? Now one case can be your entire platform is manufactured and you are going to place the fan and place the sheets on them to decide how the airflow is going to go. So there is a fan here. Okay, and then are all the motors getting equal amount of air or not is what you need to design. So this is one application on the platform side where CFD can be useful. Okay, you can simulate the entire platform in CFD and then decide that all the motors or all the components are getting the airflow efficiently or not. Second application example I can show on the uh, platform side is the operator cab. So the operator cab is where the operator sits and operates the uh, locomotive. Now in India we do not have any standards for operator cabs, but in US the standards are a bit high. The operator cab needs to have uh, uh, a toilet and it needs to be ventilated, it needs to be air conditioned. Okay, so our locos, the ones which we are supplying to Indian Railways also are ventilated and they do have air condition. So the ducting of the operator cab is also important and it takes about 5 days to get the ducting right. But if the problem is taken to CFD, you can simulate the problem on CFD and get the operator cab ducting right. Okay, within, it will take more time, but definitely on field you are sure that this type of ducting is going to give out a airflow. Same thing for this process, if done on field for the platform, takes about 12 to 20 days to get it right, okay, to get the flows on all the components right. But if done on CFD, this process can, on the field, can come down a lot. I mean, you can get it right in design stage itself. Okay, now this example, if you have the, now locos can consist. Okay, you can have 2 locos or 3 locos depending on how much load you are pulling in your freight. So if the diesel, but the second loco is of some other fuel or is a battery operated locomotive, you cannot let diesel engine affect the, so this simulation we are just getting the effluent from the diesel loco and seeing how much it is reaching the inlet, or the inlets of the battery loco are right here. So how much is reaching here. So yeah, on the cab side, this is the application. Now on the diesel engine side, there are huge amount of applications. You have a cylinder head which sits on the crankcase. You need to do the durability. So do the coolant flow thermal, where you assume the temperatures on the fire deck, and these temperatures then go to the structural model. You predict how much it is expanding according to the complicated context, how much friction is happening, and then take it to a low cycle fatigue code, calculate if any cracks are happening or not. Sorry about that. Then of course other applications go to turbocharger, getting the turbocharger map, performance map, and then exhaust for, of course, again low cycle fatigue applications. So yeah, another point I need to make is CFD alone may not be enough, and sometimes the client also thinks CFD हो गया, अभी और क्या बाकी है. So ऐसे सर अभी structural करना पड़ेगा, LCF करना पड़ेगा. So the CFD engineer should work with the structural guys in providing the loads correctly, otherwise the work gets incomplete. You need to provide the loads properly so that they can update in the models and then accurately predict the expansion or the pressures as they are distributed. Yeah, that is all from my side. Any questions? Yes, sir.
So thanks for interesting talk. Query the Indian locomotives, despite now plan to run for 160 km/h, they are almost flat front instead of like we see in others.
Yeah.
Is there any reason for specific to India, or like it works well that also?
You need to bring in innovation there. This point was very much brought up by one of the colleagues who worked on aerodynamics earlier. Brought in, why aren't Wabtec locomotives aerodynamic? Okay, there is a thought process behind it. There is no other issue. So now if you go to a Wabtec website, you will see a nicely aerodynamic loco which we are actually working after. Thanks. Nice question. Thanks.